Good day to each and everyone. Welcome to my lecture about acids and bases in organic chemistry. So it's a general chemistry subject. Now that we are taught about the three basic types of acids and bases. We have bronzed lauride and Lewis acids and bases and arrhenius. But in organic chemistry, there are just like two types of acids and bases that you could typically find. You have Lewis acids and bases and Bronsted-Lowry acids and bases. And uh, most other types of organic reactions that involve of just a transfer of proton or just proton abstraction. So reactions like this are called proton transfer reactions. And for example, you have a typical acid that is symbolized as HA, and you have water as a base. When they react together and when they reach equilibrium, the product would be H3O plus the anion of HA. So HA here is the acid, and water here is the base. Okay, so these are the products, the hydronium ion, hydronium, so H3O plus, this is hydronium. So A here, A minus is the anion of the acid. So this is a typical example of a proton transfer reaction. Ang proton, which is H plus in chemistry, ang proton ni HA na transfer sa dito kang water, thereby producing H3O plus, the hydronium ion, and the anion. Okay, so proton transfer reactions are actually, makita nimo siya sa when a bronzed-Lowry acid and a bronzed-Lowry base react together. So kung may tag bronzed-Lowry acid, this species donates a proton or proton donor. So ang bronzed-Lowry base food is the opposite. It is an acceptor of a proton, so proton acceptor. So in this typical reaction between an HA and water, HA here is the Bronsted-Lowry acid because you donate nga nga proton dito kang water. Yung siya nga H kang HA na nato siya ka water, so HA here is a Bronsted-Lowry acid, and water is a Bronsted-Lowry base. It's undergoing proton transfer reaction. In organic chemistry, it is very important that mabalaan nato ang nature of a certain compound na gina-employ nato or gina-handle nato when we do synthesis. Especially because we are concerned kung, for example, if we are adding a strong base, for example, to deprotonate a certain reagent on our reaction flask. So that is very important na mabala na ang acidity or basicity sa isa ka reagent. And in considering the acidity or basicity of a compound, whether inorganic or organic, naatay duha ka ways para mabala na to kung kani ba siya nga compound is acidic or not. The first one is the quantitative one. And this is by knowing the pKa of a certain compound. So dali ra kayo because pKa values you can just search it on Google and mabalaan na nimo dayon ang acidity sa isa ka compound. pKa values usually they are experimentally determined, of course, and given na siya from the internet. It is very easy to predict whether a compound is acidic or not just by looking at its pKa. And the lower the pKa, this means that the more acidic the compound is. Mas gamay ang pKa value, the more acidic the compound is. So that is the observed trend in these factors. So, but what if you don't know the pKa and you want to know kung kaning compound is acidic ba siya or not? There is actually a qualitative way of assessing whether or not a compound is acidic, and that is by looking at the molecular structure of that compound. And there are various factors that will help you or will serve as guidelines on how to predict the acidity of a compound just by looking at its molecular structure and without depending on the pKa. Okay, but first we are going to talk about pKa. So in acid-base reactions, normally position sa equilibrium would always favor the weaker acid or weaker base. Okay, so in a typical acid-base reaction, you have an acid and you have a base. So in this one, this is in equation 1, for example, you have a tertiary butoxide ion here that reacts with water to form the tertiary butyl alcohol here and hydroxide ion. Of course, charges should be equals in both sides, from the reactant side and product side. So in the product reactant side, -1 charge brought by this negative charge in the tertiary butoxide ion, and product side is brought about by the hydroxide ion. Okay, so going back, you have an acid here, which is a tertiary. No, that's not the acid, of course. Sorry. Sorry, this should be the base, not the acid. Here, sorry about that. So the tertiary butoxide is the base, and water acts as the acid. So the acid-base reactions normally, it is always, not normally, it should always be ang position sa equilibrium, the division mo favors weaker acid and weaker base. Okay, so ang base, mahimo siyang acid when it's been reacted with an acid, and the tawag ana niya is the conjugate acid of the base here. Ni siya. And for example, okay, I'll just label here for emphasis. This is the acid. And kaning si acid, mahimo na din siyang base. And ang tawag niya is conjugate base. Yeah. So, na siya. It's just a transfer of proton, a proton transfer reaction. Kani siyang proton, nibalhin siya dito sa base. Kaya gi-abstract man siya sa base, ikuha siya sa base from the acid. Okay, normally, ang kaning conjugate acid and conjugate bases, normally they are weaker, but not every time. Okay, it doesn't mean ang conjugate acid and conjugate base kay sila gid ang weaker version. No, that's not always the case. In order to determine the position of equilibrium, dapat dito gid siya mo favor sa weaker acid and weaker base. So, since kabalo man ta sa pKa value sa water, which is 15.7, and this is from literature actually, and ang pKa value sa tertiary butyl alcohol is 18. So, yun po ganina, the lower the pKa, the more acidic the compound is. So, which one here is more acidic? So, syempre si water, because it has lower pKa. Okay. Since uh, since higher man ang pKa ni water and si conjugate si tertiary butyl alcohol is lower man if no, sorry. Since ang pKa ni water is lower, siya ang stronger acid. And since ang pKa ni tertiary butyl alcohol is higher, therefore siya ang weaker acid. Okay. Therefore, ang position ni equilibrium dito siya mo favor sa right side. Kay mo man ang weaker acid. Ang kanaman diri nga side ang weaker acid which is tertiary butyl alcohol. So that's why the arrow, equilibrium arrow, yung nanay ang forma. So see, on a second example, number 2, same nagkatong scenario. You have here deprotonated butane and you react it with water. By the way, this is the base. And ang conjugate acid is here. And when you have water, which acts as the acid, and your conjugate base is here. So, given the pKa values, we all know that butane here, which is the conjugate acid, is the weaker acid because very high kaya ang pKa, 50. I-compare mo sa 15.7. So therefore, inani ang position sa equilibrium arrow. Favor siya sa right side. Kaya naman dito ang weaker acid. Remember that equilibrium would always favor the weaker acid or the weaker base. Always remember that. And so the third one, this is another example, but a different version. Okay. This is the base. This is acetone, by the way. And you have an acid, which is hydronium ion. This is the acid. And you have a protonated ketone here, which is the conjugate acid. Here, and the water here is the conjugate base of the acid. Okay, so based on literature, si hydronium ion na siya negative 1.74. But kanisi protonated acetone, it has a pKa of minus 7.3, which is more acidic. So therefore, obviously, it is the hydronium ion because naman siya man ang pinakagamay of pKa. So therefore, ang position sa equilibrium is towards the left. Kaya naman diri ang no, not towards the left. Sorry, the arrow that I draw is incorrect. This should be the position because you always favor the sorry. It's actually correct. The equilibrium arrow is towards the left because minus 7.3 is even lower than minus 1.74. Sorry about that. So between the hydronium ion and this protonated ketone here, this one, this is lower in terms of pKa, therefore this is the stronger acid, and hydronium ion is the weaker acid. Therefore, ang position sa equilibrium is towards the left. So, inana siya when equilibrium would favor the weaker acid always, or weaker base. So that's how you assess the acidity of a compound, not just the acidity of the compound or a molecule, but also the position of the equilibrium. And you can do it by knowing the pKa. But what if you don't have the pKa? You now go to molecular structure. And I have here an acronym called ARIO or ARIO. ARIO here stands for, this is the atom bearing the charge. R here is resonance. I is for induction. And O is for orbital hybridization. So, kanila nga 4 factors ang inyong pagkatiman-an. Atom bearing the charge, resonance, induction, and orbital hybridization. So first things first, let's talk about the atom bearing the charge. Okay. Okay. First, we talk about the atom bearing the charge. There are two ways to, there are two factors actually to consider when you want to assess the acidity of compound in terms of the atom itself that bears the charge, the negative charge. Okay. Number one is electronegativity. Electronegativity. Okay. Let's talk about electronegativity first. Suppose we have two kinds of compounds. You were asked by your professors, which one is the more acidic compound? Is it butane or butanol? Okay. Sorry. Uh, okay, this is H, for example, and here you have H here. First yung buhaton, this is the first thing that you're going to do. When you want to figure out which compound nag-compare ninyo is the more acidic, first thing that you need to do is convert them into their conjugate base first. You need to deprotonate. Okay, so when you remove a hydrogen, for example, here, minus H plus, minus H rather, this becomes here. And this one becomes no, I actually had the wrong example. This should be butanol, propanol, not butanol, propanol. Okay, so this one, this propanol should be O minus, propoxide. And we all know that this one is the, actually, this carbon ion could be written as CH2 1. So, once nga na-deprotonate na ninyo siya, na-convert na ninyo siya into its conjugate base, you need to compare the atoms na that bears a negative charge. In this case, you have carbon versus oxygen. Okay, and in the periodic table, if I will draw the periodic table here, CNOF, you have phosphorus, sulfur, chlorine here, and bromine, then iodine. But when you compare two atoms na under the same row, under the same row, the carbon here and oxygen. You have carbon here and oxygen here. So you compare the two. When they are on the same row, you need to use electronegativity. So electronegativity is the ability of an atom to attract electrons towards itself. Marag kina-attract niya ang nearby electrons padulong sa iya. So between carbon and oxygen, which is the more electronegative? Remember that the trend in electronegativity in the periodic table, from left to right, En, electronegativity increases. So therefore, oxygen is the more electronegative. Therefore, this is the more stable compound or the more stable anion, more stable anion. So when you have the more stable anion, you have the more acidic compound because in siya, an acidic compound, the more acidic, kung kisa tong acidic na compound, siya ang na ay more stabilized anion. Okay, so between the two, ang kaning propanol ang acidic. This is more acidic here. More stabilized anion, which means therefore this is more acidic. Therefore, propanol is more acidic than butane. Okay. Example number 2. This one is based on electronegativity. Example number 2. Let's go to a little bit of inorganic aspect. Okay, one atom. We now go to another factor that we consider is the atomic size. What's an atomic size? How do you use that? Suppose you have water, for example, and you compare it with hydrogen sulfide. Sorry. Okay, so first things first, we must convert these two into their conjugate base or anion. So this becomes HO minus and this becomes HAS minus by sulfide. HS minus. So you compare the two atoms that bears the charge. And this should be oxygen versus sulfur. So if we copy this snapshot of the periodic table, sorry, here, it's not anymore carbon versus oxygen, but oxygen versus sulfur. It's not along the row. It's now down a column. And when you have atoms, when you compare atoms that are down a column in the periodic table, you should use atomic size when you compare in terms of column na siya, ang iyang comparison. And according to periodic trends, down a column, atomic size increases. They increase ang atomic size. So between oxygen and sulfur, sulfur has the more size, is bigger than oxygen. So if we compare, if this is oxygen atom and this is sulfur, which is bigger, ang tendency is sulfur is more polarizable, meaning to say na mas daghan og area ang electrons na mo-flow bitaw within the space. Mas dako ang space na wherein maka-flow ang electrons or maka-move ang electrons. In other words, ma-occupy sa electrons bitaw. The bigger the size, the more stabilizing it is because of polarizability. That's the essence of polarizability. So, mas dako ang size sa atom, therefore, it stabilizes the anion. The greater the atomic size, this means that it's more stabilizing. And when you have a more stabilized anion, you have the more acidic compound. Therefore, the hydrogen sulfide here is the more acidic. This is the more acidic compared with water. So when you compare atoms along uh, along the same row or under the same row, electronegativity is more dominant. But when you compare two atoms bearing the charge down a column, atomic size is more dominant. So that's how you assess in terms of uh, uh, atoms bearing the negative charge. Suppose you have this kind of structure. Okay, so suppose if I ask you which proton is more acidic, is it the proton bonded with the N or proton bonded with the O? Okay, so first what you're going to do is you deprotonate, deprotonate, you convert the two uh, into their conjugate base. Okay, so what we're going to do is we delete this, and we have this. We have this. Okay, so we compare now the atoms that bear the charge. It's a battle between nitrogen and oxygen. So between nitrogen and oxygen, you have the periodic table CNOF. So you have nitrogen here and oxygen here, and they are along the same row. So therefore, electronegativity is dominant. En is dominant. So oxygen is the more electronegative. Therefore, it is more stabilizing. Okay? And when it is more stabilizing, it is the more acidic species. Okay, so if we write again the compound, or if we draw again the compound here, sorry, and compare which proton is the more acidic. Okay. Sorry, this proton is more acidic. Okay. Why? Simply because oxygen is more electronegative, meaning to say that the electrons along this bond and along this bond are being attracted to oxygen. And easy ni siya nga proton i-release. The more a proton is, the more easy the proton can be released, then the more acidic that proton would be. Okay, that's what you're going to think about. Mas easy siya i-release, the more acidic it is. And kaning blue proton, easy siya i-release because the electrons in this bond are more concentrated towards oxygen than hydrogen as compared to the NH bond. Okay, we have to another factor, and this one is all about resonance. Suppose you are asked to compare which compound is the more acidic. Is it going to be versus sorry, is it going to be ethanol or ethanoic acid? or acetic acid. Okay, so are we going to use the atom that bears a negative charge? If we deprotonate this, this becomes, sorry, this becomes an ethoxide, and this one becomes an acetate. So can we use the first factor? No, because they are the same atom, still oxygen. Both of them are oxygen, and that atom bears the charge. So we cannot use number one. And what are we going to do instead is to draw resonance. So the ethanol, is there any resonance going on for ethanol? No, because if you do the resonance for ethanol, then you're gonna end up like, so the first thing again, we need to convert them first into their conjugate bases. So this is the ethoxide, this is the acetate. Okay. So kung imo ning i-resonance si ethoxide, you're going to debate or sa tawag ani, imo nang gisuway si Lewis Struck, ang octet rule rather, sorry. Imo nang defy si octet rule, because remember that this carbon has two oxygens here. And if you draw a resonance, don't tell me that you will have carbon that is pentavalent. No, that, that's impossible. You have 2, 4, 6, 8, 10. 10 electrons shared. No, that's impossible. There should always be 8. And that's the octet rule. So resonance cannot happen. There is no resonance. And for this one, we can have resonance actually. So the flow of electrons would be in this pattern. Okay, so sorry. Okay, so this is the resonance forms of acetate ion. Okay, you have two resonance stabilized conjugate bases. Conjugate base. Okay, you have the acetate ion, which is the conjugate base, and it is resonance stabilized. Therefore, resonance has a stabilizing effect, and when the anion or the conjugate base is stabilized by a certain factor, and in this case resonance, uh, that the acid of that conjugate base is the more acidic one. So therefore, between ethanol and ethanoic acid, it is ethanoic acid that is more acidic as compared to the ethanol, because ethanol, on the first hand, it has no resonance. It cannot undergo the localization of its pi electrons. And resonance could happen when you have a nearby pi band, because pi band are less strong than a sigma bond, therefore it can be easily be broken, allowing the localization of electrons. So suppose you are given an example, Annie, here. Which proton is the more acidic? Is it the red one or the blue one? It is very easy just by looking at the structure. Of course, a resonance would undergo only when there's a pi bond and you have a sigma bond here, sigma, and you have pi. Right? So therefore, this hydrogen is more acidic. In this case, you cannot have resonance in this moiety here because you have no nearby pi bond. And when you do resonance, when you draw the resonance structures, you are gina-deviate nimo ang octet rule. So if we draw the conjugate base or the anion of this, for example, here, you cannot do resonance because if you do, then you are not following the octet here. Remember that carbon has carbon is tetravalent, and when you add up like electrons here, this becomes the carbon becomes pentavalent, and that's impossible to happen. So therefore, there's no resonance here. So since this nitrogen, this proton which is attached to nitrogen, is can undergo resonance because this is an amide functional group, and amide functional group has pi bond. And when we draw the resonance form, this one, say here, electrons are being delocalized. This pi bond is trapped now in the nitrogen from oxygen, and yeah, that's what happens. So there is resonance in here. So just a quick tip: when you see a nearby pi bond, then that's when you know na nanay resonance na may tabuana. So that's how you assess in terms of resonance. Now we go to the third factor, which is induction. Others would call this inductive effect. Okay, so what if you have two compounds? Okay, so first we check or we deprotonate and convert them into their conjugate base. This is the first thing that you're going to do always. Okay, so can we use the atom bearing the charge to compare? No, because they are the same atom, oxygen, that bears the charge. So we cannot rule out this one in terms of the atom bearing the charge. Can we do resonance? No, because both of them could undergo resonance because both of them has a nearby pi bond here. We cannot rule out they will contain the same resonance structure. And by the way, when you have two compounds, we compare two compounds that can undergo resonance structure. With ang katong compound nga naay mas daghan og resonance structure or contributing structure, mo to siya ang more acidic as compared to the other. That's always the case. Okay. So, uh, so again, we cannot rule out this in turn using the second factor, which is resonance. So we now go to the third factor, which is induction or inductive effect. Inductive effect is just it's like a property or an effect na mura bitaw manghina or maghina or magaway electron density sa usa ka uh, portion sa isa ka molecule due to the presence of electronegative atoms, adjacent electronegative atoms. So, of course, here, if we compare the conjugate bases, di ba makaingon man ta na at this part here, mo na siya ang portion sa duha ka conjugate base nga naay dako og electron density because this is negatively charged. You have lots of electrons there. Here, this is the portion sa structure na daghang electrons. So what happens is that in reality, ang kani siya nga oxygen is lower in terms of electron density as compared to this. Why? Because of the presence of these three chlorine atoms, which pulls away electrons. Towards themselves. Here. Wala siyang inductive effect. So, since chlorine is more electronegative than oxygen, gina-attract niyang electrons from this oxygen towards themselves, thereby decreasing electron density in O minus is decreased. Okay, electron density in this oxygen atom is decreased, as well as there is also a portion of this carbonyl here nga mag-decrease ang electron due to the presence of these three chlorine atoms which are electronegative, and that's what we call inductive effect, and it is stabilizing. Remember that any stabilizing effect will lower the energy. That's why it's stable. When you have stability, that would always constitute lower in energy. And when you have a more stabilized compound, this is more stabilized, by the way, as compared to the other one. So when you have the more stabilized conjugate base, that means it's acid. The acid of that conjugate base is the more acidic one. So therefore, comparing acetic acid and trichloroacetic acid, trichloroacetic acid is the more acidic. And you can actually compare that when you have chlorosubstituted acetic acids. Okay. For example, you have acetic acid here. You have 4 acetic acid. The greater the number of electronegative atoms in the compound, the more acidic the compound is. Here. So acidity increases as the number of electronegative atoms is increasing in a given compound. So that is inductive effect. So lastly is the orbital of the compound. The orbital of the orbital hybridization, actually. Suppose you have orbital hybridization. Okay, so suppose you have this kind of compound. Here. Suppose you have that one. Okay, so if you compare the two hydrogens or the two protons, which proton is more acidic? Okay. That could be answered by the hybridization of the conjugate base. Okay, so first you are going to convert them into their conjugate bases. Negative charge. Okay, so you'll now have the conjugate bases. Anisha. So remember that carbon-carbon single bond is sp3 hybridized. Carbon-carbon double bond is sp hybridized. Carbon-carbon triple bond is sp2 rather, for the carbon-carbon double bond. And carbon-carbon triple bond is sp hybridized. Remember that. I should just move this a little bit. Okay, so if we compare the percent S character, this is 50% S character, and this one is 33% S character, and this one is 25% S character. The higher the S character, meaning to say the stronger the bond is. Okay. The higher the S character, the more stronger the bond. Why is S character the determining factor? Because ang S character, mo na siyang orbital na closer sa nucleus. And when you have higher S character, and in this case, the triple bond here has higher S character, 50% compared to 33%. Meaning to say, ang kaning electrons ani na conjugate base here, mas doon siya sa nucleus sa atom. Okay. Because it has higher S character. I-compare nimo sa double bond na 33% lang. And remember that the S orbital is mas inner siya compared kay p orbital, and mas duol siya sa nucleus compared kay p orbital. And when we compare the orbital representation of the two, example, this is the, for example, if this is the sp3 orbital, this is the sp orbital. And CSP3, this is sp2 by the way, and CSP is a little bit wider. Ano yung orbital representation? Mas dool siya sa nucleus ang sp orbital. Mo ng electrons na naa ng sp hybrid orbitals. By the way, this is the hybrid orbitals. Here. Mas taas ang S character, the more na mas closer sa nucleus ang electrons. So therefore, ang electrons na naa hybrid orbital are more stabilized. And when it is more stabilized, therefore for the corresponding acid of that conjugate base is the more acidic one. Therefore, this proton is more acidic compared to this red proton here because of the sp hybridization of this of its conjugate base. Mas dali niya i-release ning blue nga proton tungod kay ang kaning electrons diri mas intact, mas stabilize siya sa protons sa nucleus. They are readily attracted towards the nucleus of the atom as compared diri sa double bond because it only has 33% S character. Okay. Mas dali niya buy-an ning blue proton as compared when this carbon releases this red proton. And osbo na ko kung unsa ka paspas or unsa ka dali buy-an ang proton, meaning ana the more acidic ang proton. That's the concept of acid base. It's just the extent of it's also an extent of how easy a certain atom could release the proton. So that's it. And if we summarize the REO, summarize everything, ARIO. Okay, you have two ways of identifying which compound is the more acidic or not. The first one is the quantitative, which is very easy. You just have to find or search the internet and look at its pKa. The lower the pKa, meaning to say the more acidic the compound is. That's easy. And the higher the pKa, the more the equilibrium will be favored towards the compound with higher pKa because it's the weaker acid. It's favored. Okay, that's the concept of pKa, and it's quantitative. It's very easy. You just have to search the internet. But when you don't know the pKa, you just use the molecular structure, and it is the qualitative way. And you can use them by REO, which is atom, and you can do two factors. One is electronegativity, the other one is atomic size. And electronegativity is when you compare two atoms that bear the charge and the position under the same row. So electronegativity is dominant. But when you compare two atoms bearing the charge and they are under the column, atomic size is more dominant. The higher the electronegativity of the atom, the more stabilized the anion is, and the more acidic the compound is that corresponds to the anion. And the larger or the greater or the bigger the size of the atom is, the more stabilizing it is. And the more stabilized is the conjugate base, and the more acidic is the corresponding acid. So the second one is resonance. Whichever has resonance is the more acidic compound, and you can just determine easily which species undergoes resonance by just looking with whether or not there is a nearby pi bond. And the greater the number of resonance structure, the more acidic the compound is. So the third one is inductive effect. Higher electronegative atoms, meaning to say more acidic, because the presence of electronegative atoms in a compound would tend to decrease the electron density in the molecule because of its electronegative nature. And the last one is orbital hybridization. station. The higher the percent S character, the more acidic the compound is. So in terms of acidity, the trend would be here, increasing acidity. So that's the trend. So these are the two ways that you can use in order to determine whether or not the compound is acidic, and when you want to compare which compound is the more acidic or the less acidic. So that ends my presentation. I hope you enjoy listening.